Hello and welcome to the logic of it all. In this video, we are going to talk about how we can design a finite state recognizer. And we are going to do this through 4 examples. And the idea behind all these examples is we are given the specification of a finite state recognizer, which means we are given the description of all the strings on a given alphabet that is supposed to be accepted by the machine. So we know exactly which strings over that alphabet should be accepted and which strings should be rejected. And then the task is to design a finite state recognizer that does exactly that. Now, here's our first example. So the alphabet in this example is 0 and 1, so it's binary. And the machine that we want to design is supposed to accept any string over 0, 1, so any binary string that somewhere in that string we see the substring 0, 1, 0. And that could be in the beginning, in the middle, or at the end of the string. But as long as the pattern 0, 1, 0 occurs somewhere in that string, it should be accepted. And if 0, 1, 0 doesn't occur anywhere in the input stream, then it should be rejected by the machine. And there are different ways that we can go about this task of designing a finite state recognizer. And I will try to explain each one of these ideas through these examples. And one of the ideas is we first start by designing a machine, the part of the machine, let's say, that accepts the shortest string that is supposed to be accepted. Let me explain. So given this description that the machine is supposed to accept every string that has 0, 1, 0 somewhere occurring in it, the shortest string that you can imagine that has that property is 0, 1, 0. So 0, 1, 0 is obviously a string that the machine must accept, and it's the shortest such a string, right? So we focus on this aspect first. We design the part of the machine that does that accepts 0, 1, 0, and then amend that and add more, if needed, more nodes and more edges to cover the other cases as well. So if you want to follow this approach, then we say, okay, we should start from some initial state. So let's call that initial state 0 or 1. Let me try to draw a better circle. So let's say this is a state 1 and this is our initial state, and we want to design the part of the machine that is responsible for accepting exactly the string 0, 1, 0, because this is the shortest string that will be accepted by the machine. So with a 0, we go to a state, let's call that 2, and then with a 1, we go to the next state, let's call that 3, and then with another 0, now our 0, 1, 0 is complete, so we go to another state. I'm going to call that state number 4, and this is an accepting state because 0, 1, 0 is a string that is, based on the description, must be accepted by the machine. Okay, and so obviously this is not a complete finite state machine. We need to still add more transitions, more edges, and sometimes we need to add more vertices, more nodes as well. But we will do that by looking at other possibilities rather than just focusing on the shortest string that must be accepted by the machine. Okay. Now, another thing that helps when you are designing this, and again, through these examples, I re-emphasize on this fact, is to remember that these states that we have in the machine represent what the machine remembers, that those are the states of the memory of the machine. So if you are at the state 1, so what you should remember, what you should imagine about the state 1 is that we have not seen any part of the pattern 0, 1, 0 yet. Or, saying it in a different way, we are waiting for a 0 followed by a 1 followed by a 0 to get to the accepting state, right? So if you have a 0 followed by a 1 followed by a 0, then from state 1 you get to state 4. So being at the state 1 means that we are waiting for a 0 followed by 1 followed by 0 to accept, to end up with in an accepting state. Similarly, if we are at the state 2, the intuition behind state 2 should be that we have seen the 0 in the pattern 0, 1, 0, the first 0. In other words, we are waiting for a 1 followed by a 0 to get to the accepting state. As you can imagine, while you are here at 2, if you see a 1 followed by a 0, you get to the accepting state. And finally, if you think about the state 3, it means that we have seen the first two parts, the first two symbols in the pattern that we are looking for, the 0 and the 1, and we are waiting for the next symbol to be a 0 to finish the pattern and get the 0, 1, 0. So being at the state 3 can mean that the last two symbols that we have seen are 0, 1. Another way of saying the same thing is if we are at the state 3 and the next symbol that we read is a 0, then we are going to have a stream that will be accepted. So now let's complete the finite state machine that we have designed part of it so far. Now, if we are at the state 4, we don't have any transition for state 4 yet, but we know that we want the pattern 0, 1, 0 to occur somewhere in the string. And if we are at 4, it means that that already has happened, which means whatever follows after that is not going to change our final decision. The machine is going to accept the string no matter what comes next. So if we are at 4 and we read a 0, we are going to stay at 4 because still the string contains 0, 1, 0. That is already established. What follows is not going to change the fact that 0, 1, 0 has already occurred once in the string. And similarly, if we are at the state 4 and the next symbol that we see is a 1, we are going to stay at state number 4. Now, sometimes when we have two edges that do exactly the same thing from the same state to the same state, we can combine them into one edge and then use both labels on that edge. So this edge is for transition from 4 to itself, whether the next symbol is a 0 or a 1. Now, the transition for 1, 2, 3 is also incomplete. So for example, we need to say something about what if we are at the state 1 and instead of a 0, we read a 1. Now, if we are at state 1, it means that we have not started seeing any part of this pattern 0, 1, 0 yet. And if we see a 1, that's not going to contribute anything to this pattern 0, 1, 0 because what we need first is a 0. So it means a 1 is not going to help us improve, and that means we are going to stay at state 1. Similarly, we need to figure out what happens if we are at state 2 when we read a 0 and 3 and we read a 1. Okay, so let's just start here. We are at state number 2, which means what? Which means that the last symbol that we have read is a 0. Now, if we read another 0, so we have the last symbol, so we have read some stuff, and then we have read a 0, and that's why we are at state 2. The last symbol that we have read is a 0. And that might have been followed by either 1, 1, or a bunch of 1s or no 1s, but the last symbol is a 0, and we are waiting for the next 1 and the next 0 to accept. Now, if we read another 0 here, that's not going to help us improve in the pattern that we are looking for, but it doesn't take us back any step either, because still the last symbol that we have read is a 0, and with a 1, 0 we can finish. In other words, with a 0 we are going to stay here waiting for the next 1 and the next 0 to accept. And finally, if you are at state number 3, which means what? Which means that if you are at state number 3, it means in the pattern 0, 1, 0, you have already seen the 0 and the 1, the 0 and the 1. That's why you are here. And you're waiting for the next 0 to finish it up. But what if instead of a 0, you see a 1? Now you have 0, 1, 1 as the last three symbols that you have read. And that completely interrupts the pattern 0, 1, 0. And we need to start with another 0, which means we have to start over from the beginning. And that's why with a 1 from state 3, we go back to state number 1, because now we need to read a 0, a 1, and a 0 to get to the accepting state. And that is the finite state machine that we need for this problem. Now, a cleaner version of that, same thing, would be here with 4 states. The state number 4 is the accepting state. State number 1 is the initial state, and with all the transitions for any of the symbols in the alphabet. Now, moving on to the next example with a little bit of more applied flavor. So imagine a programming language where if you want to choose a name as an identifier, the name must start, the identifier must start with a letter. And so it means that it cannot start with a digit. It cannot also start with another symbol like a question mark or a period and so on. So it must start with a letter. And what follows next is it could be that that first initial letter is followed by more letters or digits or not. So it could be just a single letter. That's also acceptable. And that is it. So for your identifiers, you can just have a single letter. So something like B is acceptable as one letter followed by 0 more letters and digits. It could be that B is followed by other letters or digits in any combination. And that's it. These are the type of identifiers that are allowed. And our alphabet is all the ASCII characters. Now what we want to do is we want to design a machine that exactly accepts the identifiers that are acceptable by this specific programming language. So again, we start from an initial state 0, let's say. Now the first thing we know is that if the first symbol, or let's start with accepting one, again, similar to the previous one. So the first thing that we expect in an identifier is a letter. And it could be that that's just enough, right? The shortest, given that description, the shortest identifier that is acceptable is just a single letter, right? If you read the description, it could be that your identifier is just N or A or B and so on. So with a single letter from your initial state, you get to state number 1 and you accept. That's the simplest kind of thing that can happen. Now we amend this by looking at other possibilities. So for example, if you have read the first symbol in your input and that's the letter, and then you're here at state number 1, and then there is more to your input stream. Maybe there are more letters. Now, if you think about it, still that is acceptable because that initial letter may be followed by 0 or more letters. So if I am at state number 1 and I read another letter, that's perfectly fine, right? So with a letter, I stay there. It's also allowed that that initial letter is followed by digits. So if the next symbol is a digit, still I stay at the state number 1, and that can happen as many times. So it could be that the initial letter is followed by another letter, and then a digit, and then another digit, and then another letter, and so on, any combination as the question requests. So there's that. Now, the other possibility that we need to consider is, what if we are at state 0, and the first symbol that we read is something that is not a letter, maybe a digit, or maybe a question mark, or underscore, and so on. So any non-letter symbol, non-letter character. And if you read the description again, that immediately disqualifies your input. No matter what follows, that input, if it starts with a non-letter character, is not going to be accepted no matter what follows. So for these type of cases, we introduce an error state. Okay, so you can call it state number 2 or something, but I call it state error because if you get here, and in this case, we get there if we see a non-letter symbol at the beginning as the first symbol in our input stream. Now, the idea of an error state is if you get here, your input stream is doomed to be rejected, no matter what follows. In other words, if you are here, any character that you read after that, you are going to stay in the error state, right? So if you start with a non-letter, no matter what follows, you are going to end up at the error state, which means you are not going to reach to the state that is an accepting state, and you are going to reject that input. Now, the final thing that we need to talk about is what if we are at state number 1, which means we have seen the initial letter, and that initial letter may have been followed by more letters and or digits, but then we see a character that is neither a letter or a digit, maybe a question mark, or maybe a comma or something like that. And again, based on the description, that is not allowed in an identifier, which means that if you see any character like that, then immediately you go to the error state, which means you are not going to ever end up in the accepting state. So anything except a digit or a letter takes you from state number 1 to the error state. So let's say non-alpha numeric. And that's it. That's the finite state machine that um, accepts exactly the identifiers that are explained in the question. And here's the transition diagram, exactly what we talked about, and the corresponding transition table, where we have 3 states, state 0, state 1, and the error state, and we have 3 possible categories for our input. So letter, all the letters A, B, C, and so on. If you are at state 0 and you read the letter, you go to state 1. If you are at state 1 and you read the letter, you stay at 1. And if you are at the error state and you read a letter, you stay at the error state. And similarly for the other 2 types of input, digits, so from 0 to 9, and non-alphanumerical, so exclamation point, comma, any other character that you can imagine, question mark, and so on. So this is the transition table, and this is the transition diagram for the finite state recognizer, for example 2. Now, moving on to the third example, this is kind of along the similar lines as the previous one. This time, the strings that we want to accept are a combination of a combination of lowercase letters, and then that combination may immediately be followed by a period, and that is acceptable. Or it could be that a combination of lowercase letters followed by a comma, and then another combination of lowercase letters, maybe followed by another comma, and then another combination, and so on. And you can have as many of them as you want. It could be just one, and in that case, you don't have a comma, you end with a period. You can have 2, 3, 4 of these. Let's call them words, right? So you can have 2 words separated by a comma, and then ended with a period, or 3 or 4 or 5, and so on. And these are the only things that the machine is supposed to accept. And we are assuming that our alphabet is lowercase letters plus comma plus period. Okay, so we want to design a finite state machine that exactly accepts these type of strings. So again, let's start with an initial state. So this is state number 0, our initial state. Now, if we start with the letter as the first symbol, that takes us to state number 1. And the shortest string that this machine is supposed to accept is a letter, let's say the letter B, followed by period, right? We must have the period to accept. This is not enough to just have the letter. So with a period, we get to state number 2, and that's the shortest string that is accepted. Now, if you are at the state number 1, which means that we have read one letter, it could be that we read more letters after that. So after B, instead of period, we read A, and then C, and then D, and so on. And that's perfectly fine. And still, after that, we can end up with a period, and we accept. So with more letters, we stay at state number 1, waiting for that period to finish it up, and we end up at state number 2. Now, it is also possible that after reading the first letter and maybe more letters, while we are at state number 1, we read a comma. And when we read a comma, that takes us back to state number 0. So takes us to state number 0 because then with more letters we are back to state number 1, and then a period can end us at state number 2 and accept. Now the bad cases, so this covers the cases that we are going to accept, but there are other cases that, immediately we realize that this stream is not going to be accepted no matter what follows. So one case is if we start with a period. That's not allowed, right? Remember, we must have at least one letter or a combination of letters before the period. So if we see a period dot as the first symbol, that immediately takes us to the error state, which means whatever follows, we are not going to get out of that. So any character, we stay at the error state. And similarly, if we start with a comma before reading any letters, still that takes us also to the error state, because no matter what follows, if the first symbol in your input stream is a comma, whatever follows is not going to make it okay and it will be rejected. So that takes us to the error state as well. And finally, if we are at the state number 2, which means that we have seen a combination of letters, maybe followed by a comma and more combination of letters, and this can happen either once or multiple times, and then followed by a period, and we got to the accepting state. Now, if you read the description of the machine, nothing should follow the period. Period should be the end of the input stream, which means if you are at the state 2 and you see anything after that, that's not acceptable, and that will end up with a stream that is going to be rejected no matter what. So with any character from state number 2, we get to this state, the error state, and we are going to stay there no matter what follows after that. So here's the machine that exactly accepts the strings that are described in example 3. And finally, our last example. This time our alphabet is AB, and this example here is because sometimes we want to design a machine that covers 2 patterns. So in this case, over the alphabet AB, we want to design a machine that accepts 2 types of inputs. Those inputs that start with the letter B, so it can be B followed by anything, or it could be that they do not start with a B, so they start with the letter A and end in AB. Okay, so it should either start with a B and then no matter what follows, or if it starts with an A, it should end with AB to be accepted. So 2 separate patterns, and both of them should be accepted by the machine. Now, how do we implement that? So again, we start with the initial state, thinking about the shortest input that can be accepted. The first pattern says if it starts with a B, no matter what follows should be accepted. So it could be that it's just a B and that is acceptable. So with a single B, we get to state, let's say number 2, and this state is an accepting state. And the other thing that we immediately notice is that if it starts with a B, according to the description, no matter what follows, it must be accepted. So if you are at the state number 2, anything can follow and you are going to stay in the accepting state and accept at the end. So that's one branch, that's one type, the first type. Those that start with the letter B are covered here. Now, there is another possibility that your input starts with the letter A. So what do we do there? So first of all, when we read A, we go to a different state, let's say state number 3, and this state means that our input started with an A. Now, again, if you think about the second type, the shortest string that is accepted, in other words, the shortest string that ends with AB is AB itself. So if we are at 3 and we read a B, we go to a state, let's call it state number 4, and accept, if our input is just AB. Now, it's possible that we are at 3 and instead of reading a B, we read another A. So instead of just a single A, now we have 2 A's. But still, that can be followed by a B and be accepted. In other words, with an A, we stay at this state and waiting for that B to finish it up and accept. Now, the other thing that we need to think about is what if we are at state number 4, which means what? Which means that what we have read so far is either a single A or maybe multiple A's through this loop here, followed by a B. So we are dealing with something that looks like either this, or this, or this, and so on. And so one or more A's followed by B, and we are at the state number 4. And now we read another A. So we have one or more A's followed by a B, and then we read an A. So we are at state number 4, and then we read the A. What should we do? So you see that again, if A is the last symbol that we have read, it's possible that with another B, we accept again. So we are exactly in the same situation as state 3. So another way of saying this is with an A, we can simply go one step back to step 3, waiting for this B to finish this up and accept again. Now, there is another possibility that we are at state number 4, which means that our input stream so far has ended with AB, so other stuff followed by AB, and now we see a B. Now, this B, that's a different story, because if we see a B, now, first of all, we know that our input started with an A because we are in this branch. That's how we ended up at state 4. Must have started with an A, and then other combinations of A and B has occurred in between. Now the last two symbols were AB, that's why we were at 4. Now we see another B. Now for this string to be accepted now, what we need is an A followed by a B. But none of the existing states represent that. So what we need now is another state. So if we are here and we read a B, we need to go to another state that I'm going to call state number 5, which is the state that the input stream has started with A, but now we need an A followed by a B to accept. Okay, so if we get that A, which means that now we can go here and wait for the B to finish this. And if we are here and we read a B, it means that we still are waiting for an A followed by a B to accept. So this is the finite state machine that does exactly what the description requests.